Welcome to EDU World Space.
The Compton effect is one of the ways the particle nature of photons makes itself evident. And in the Compton effect, you basically have a billiard ball collision between an incoming photon and some sort of particle. We usually look at electrons, and we'll see why in a little bit. One of the main reasons is they are free in many metals, or very nearly free. But the photon comes in with a certain energy and momentum. It bounces off the electron. Let's show it at a glancing angle. But there's a wide array of angles that it could bounce off on. We'll call that angle theta. And of course, a glancing blow, the electron will go off at some other angle. So you can detect the outgoing photon, and you will see that its momentum has changed because the wavelength has shifted. And the difference between the outgoing wavelength and the incoming wavelength can be measured. It is a measurable difference, theoretically given by this Compton relationship. Okay, so that wavelength shift is a function of the angle that you place your detector at. Now, this cluster of constants out in front is called the Compton wavelength. We'll see what consequence that Compton wavelength has if you are seeing a collision between a photon and an electron versus a photon and a proton. Yes, that will matter. So let's start off with the electron. What we basically have, I will use good old atomic units. The cluster HC, 1240 eV nanometers. The rest energy of an electron in electron volts. And that comes out to be, let's see, of the order of a couple times 10 to the minus 3 nanometers. And let me write that in picometers. Yeah, let's just call it a picometer times 10 to the minus 12. Picometers tend to be in the X-ray region of the spectrum, which means that the best place to see Compton scattering for the electron would be in the X-ray region or shorter. And same with lambda prime. Lambda prime will be in the X-ray or shorter. Okay, so that has consequences for what type of source of electrons you would need. Either a gamma ray source or an X-ray tube. So let's take a look at protons. Let's take a look at what the Compton scattering wavelength, base wavelength, would be if you were bouncing off of a free proton. So again, we just use the atomic units and put in the rest energy of a proton. And that comes out to be a very small amount of even picometers. So that is an extremely short wavelength, and you would basically need to have your incoming wavelength in the far gamma ray part of the region, or shorter. Well, there is nothing shorter than a gamma ray, so you're kind of stuck there. And lambda prime also in the gamma ray. Can't write gamma here. And the shift will be just a little bit longer than the incoming ray. So you could operate at longer wavelengths, but you would need a spectrometer with exceedingly high resolution in order to be able to see the outgoing wavelength. So yes, which particle you are having a collision with will determine what part of the spectrum that you want to make your observations in, and whether the resolution is going to be difficult to achieve